Today we're going to talk about 2's complement integers and also about hexadecimal or base 16 numbers. When we do pencil and paper arithmetic, we use plus and minus signs to represent positive and negative numbers. Although we can display or print plus and minus signs with computers, there's no internal representation of plus or minus. We have only the symbols 0 and 1 internally, and so we need a way to represent negative numbers using only zeros and ones. One possible solution is this format called signed magnitude. We use one bit of a binary number to represent the sign, and the remainder of the bits to represent the magnitude. So consider an 8-bit number. If I use one bit for the sign, there are 7 bits left to represent the magnitude of the number. We choose 0 to represent a plus sign and 1 to represent minus. I still have the same number of values, that is 2 to the 8th is 256 for 8 bits, but I can only count about half as high. Why is that? Right, I've only got 7 bits for magnitude. There are a couple of more problems with signed magnitude. If we have a 0 and 7 ones, that's a plus 127. A 1 and 7 ones, that's a minus 127. But what about 0 and 7 zeros and 1 and 7 zeros? The 0 and 7 zeros is a plus 0. The 1 and 7 zeros is a minus 0. We have 2 values for 0, and that's bad because we frequently compare to 0 in computer programming. Also, arithmetic on signed magnitude numbers is different than arithmetic for unsigned integers. That's also bad. We'd like for our arithmetic to stay the same. We will see signed magnitude numbers when we talk about floating point next time, but for integers we do something different. That something different is called 2's complement. We're going to use about half the possible values for positive numbers and the rest for negative numbers. Non-negative numbers in 8 bits, 0 and 7 ones, that's a plus 127. 0, 6 ones and another 0, that's a plus 126. 0, 6 more zeros and a 1, that's a plus 1. 8 zeros is 0 and there's only one of it. Even better, addition, subtraction, and multiplication are the same as for unsigned numbers. With 2's complement numbers, that leftmost bit, which we call the sign bit, represents a negative number times the power of 2 indicated by the position of the sign bit within the number. The remaining bits represent positive values added back to that negative value. So let's look at that using sigma notation. I have minus a sub n minus 1 times 2 to the n minus 1 power. That will be the most significant bit. Then I'm going to add back, there's a plus sign there, the sum from I equals 0, and this time we go only to n minus 2, because we already used n minus 1. The sum from I equals 0 of a sub I times 2 to the I power. So let's look at some negative numbers. Here are the same positive numbers we looked at a moment ago. 8 ones is a minus 1. And that might cause you to say, what? But it's really quite easy. That leftmost one is a negative 128. And then we have 7 more ones, 127, added back. And it turns out that no matter what size a 2's complement number is, all ones represents minus 1. 1 less than that is a minus 2. A 1, 0, 0, 0, 0, 0, and a 1, 0 is minus 126. A 1, 6 zeros and a 1 is minus 127. A 1 and 7 zeros, that is a minus 128 with nothing added back, represents a minus 128. So let's look at some more of those. A 1 and 7 zeros is a minus 128 plus 0, and that's a minus 128. A 1, 6 zeros, and a 1 is minus 128 plus 1. That's a minus 127. A 1, 5 zeros, and a binary 2, minus 128 plus 2, that's a minus 126, plus 3 is a minus 125, and so on until we get to minus 128 plus 127, and that is a minus 1. If you need some more convincing, those 7 ones are 2 to the 7th minus 1. It's the same as 64 plus 32 plus 16 plus 8 plus 4 plus 2 plus 1, and that is a 127. Now there is a problem with 2's complement. It's not as bad as the problems with signed magnitude, but there is a problem with 2's complement. In 8 bits, the biggest number we can represent is a plus 127. But the most negative number we can represent is a minus 128. The largest positive number, plus 127, largest negative number, minus 128. There is one more negative number than positive numbers. Why is that? Well, we include 0 in the positive side. For a number of any size, we have an even number of values, and 0 takes one of those away, leaving us an odd number of values for the positive values, but an even number for the negative values. So let's look at that another way. Every binary number has 2 to the n possible values. N is the number of bits, so it has to be greater than 0, and 2 to the n is even for any n greater than 0. 2, 4, 8, 16, 32, and so on. 0 is the first positive number, but minus 1 is the first negative number. The negative half does not need to include 0 and should not include 0. For 8-bit integers, the largest positive number is 127, the largest negative number minus 128, and we say that 2's complement numbers are asymmetric about 0. There's one more negative value than there are positive values. Asymmetric about 0. In order to use 2's complement numbers, we have to talk about complementing a number. Complementing has the effect of multiplying by minus 1 or subtracting from 0. They're both the same thing. The definitive way of complementing a number is to complement, that is to flip each bit. If a bit was a 1, make it a 0. If it was a 0, make it a 1. And to the result of complementing each bit, we add 1. This is effectively subtracting the number to be complemented from 0. The trick is that we're going to subtract from minus 1, that is all 1s, and then add 1 to it to effectively subtract from 0. So let's look at subtracting from minus 1. Remember, all 1s is a minus 1 in 2's complement. If I subtract our old friend 10111, and I represent it with 8 bits, 000101111, and subtract from minus 1, I get 1110100. If I flip each bit of 000101111, I get 1101000. Complementing, that is, flipping each bit and subtracting from minus 1, produce the same result. We're not done with complementation yet. We still need to add 1 to that complemented number. So let's find the 2's complement of our old friend 000101111. That's a 23 base 10. First, we complement each bit and get 1110100. I add 1 to that, and there's nothing to carry in this example, so I get 111010001. I can check whether that worked by adding the plus 23 to my minus 23. So So here's the minus 23 we obtained by taking the 2's complement, and there's our old friend plus 23. 1 plus 1 is 0 with 1 to carry. 1 plus 1 is 0 with 1 to carry. 1 plus 1 is 0 with 1 to carry. 1 plus 1 is 0 with 1 to carry. 1 plus 1 is 0 with 1 to carry. 1 plus 1 is 0 with 1 to carry. 1 plus 1 is 0 with 1 to carry. And you're getting tired of this by now, but 1 plus 1 is 0 with 1 to carry. That carry out of the left is discarded because we're working with finite precision arithmetic, in this case 8 bits, and so minus 23 plus 23 is 0, just as we expect. Complementation works both ways. Here's minus 23 base 10 expressed as a 2's complement number, 111010001. I'm going to complement each bit, and then I'm going to add 1. And I get 0001, 0111, the same plus 23 that we expected. So if I complement a negative number, if I take the 2's complement of a negative number, I'll get a positive number. If I take the 2's complement of a positive number, I get a negative number. Now, that was the mechanism for finding the 2's complement by subtracting from 0. There is a shortcut, and the shortcut is this. Copy the bits of the number from the right until you have copied a 1 bit, then complement, that is, flip the remaining bits. So let's look at that. If I want to take the 2's complement of 001, 0111, I copy from the right until I've copied a 1 bit. That's the first one this time. Then I complement, that is, flip the remaining bits, and get, reading from the right, 0010111. If I do the same thing by the standard method of flipping the bits and adding 1, I get the same answer. Let's look at one where the first 1 bit is not the rightmost bit. Take the 2's complement of 000111010. I copy from the right until I have copied a 1 bit, and I do copy that 1 bit. Then I flip or complement the remaining bits. And here it is done the standard way. This works because adding 1 to a binary number is accomplished by flipping all the 1's to 0's from the right until a 0 is reached. Flip that one to a 1 and stop, essentially carrying the overflow of adding 1 to 1. So one method only flips the bits to the left of the first 1, while the other method, the first method, flips all the bits and then adds 1. 2's complement addition uses the ordinary rules of binary addition. That is, I can add 2's complement numbers the same way I would add any binary integers. Any carry out of the leftmost bit is discarded, but usually we build computers so that a flag gets set in the case of that carry, and we can that way do arithmetic on more than one word. We're working with finite precision arithmetic on numbers of fixed size, and so overflow can occur with 2's complement numbers just as it can occur with ordinary binary integers. Overflow is a result that is too large to fit in the available space. That condition of overflow produces an incorrect result. For 2's complement numbers, there is an overflow rule that has 2 parts. The first part of the overflow rule is that if 2 numbers of opposite signs are added, overflow cannot occur. The second part of the rule is if you add 2 numbers of the same sign and get a result that is of the opposite sign, something is wrong, and that something is that overflow has occurred. Addition is commutative, that is, 5 plus 3 is the same as 3 plus 5. Subtraction is not commutative. 5 minus 3 is not at all the same as 3 minus 5. The first number in a subtraction problem, the number being diminished, is called the minuend. The second number, the number being subtracted, is called the subtrahend. So the first number is the minuend, the second number is the subtrahend, and the result is the difference. And there's an example on the screen. Having defined minuend and subtrahend, we can now state the subtraction rule. Form the 2's complement of the subtrahend and add it to the minuend. That's good news because it means we don't need to build special circuits to do subtraction. All we need is the circuits we would need anyway for complementation and addition. Another thing about 2's complement numbers is sign extension. So here we have an 8-bit binary number, 000101111. I can add another 0 on the left, and those two numbers are clearly equal. That 0 on the left, the 0 that was added on the left, is not significant. I can store positive numbers in a larger word by adding zeros on the left. If I want to store an 8-bit number in a 16-bit word, I just add 8 zeros on the left. For 32 bits, I'd add enough zeros to get to 32. Now, let's consider this signed 8-bit number. There's a 1 bit in the sign bit, 111010001. It turns out, and you can prove this to yourself, that 111010001 is exactly equal to 111101001. The sign bit multiplier becomes larger. It becomes minus 2 to the 8th instead of 2 to the 7th. But the difference is exactly offset by the additional 2 to the 7th added back. I can add more 1 bits on the left without changing the value, and I can add as many of those 1 bits as I need. That leads us to the sign extension rule. I can store a 2's complement number in a larger space by extending the sign bit on the left. If the sign bit is a 0, I add zeros on the left. If the sign bit is a 1, I add 1s on the left. You can also remove bits from the left as long as removal doesn't change the sign bits. So we learned a couple of things about binary numbers and 2's complement numbers today. For 2's complement integers, the leftmost bit tells whether the number is positive or negative. 0 is a positive number, 1 is a negative number. For both unsigned and 2's complement binary integers, the rightmost bit tells whether the number is even or odd. If that rightmost bit is a 0, the number is even. If the rightmost bit is a 1, the number is odd. There are some limitations of 2's complement. Only integers, that is whole numbers, so no numbers smaller than 1 but greater than 0. We can't store really big numbers. With 32 bits, that's about plus or minus 2 billion. Now remember that 2 to the 64th is about 1.8 times 10 to the 19th, or 18 quintillion. If that number is signed, we get about 9 quintillion. That's a really big number, but we still can't store really, really big numbers. Things are better with 64 bits, but still not good enough for all of our possible needs. So let's summarize 2's complement. I can represent both positive and negative integers. 2's complement numbers are asymmetric about 0. There is one more negative value than there are positive values because 0 is part of the positive values. I can form the 2's complement by flipping the bits and adding 1, or by copying from the right until I've copied a 1 bit, and then complementing, that is, flipping the remaining bits. The overflow rule has 2 parts. First, if two numbers of opposite sign are added, overflow cannot occur. Second, if two numbers of the same sign are added and the result is of the opposite sign, overflow has occurred. The subtraction rule is take the 2's complement of the subtrahend, the number being subtracted, and add it to the minuend. The sign extension rule says that we can store a 2's complement number in a larger space by extending the leftmost bit on the left. So if that leftmost bit is a 0, I add zeros on the left. If the leftmost bit, the sign bit, is a 1, I add 1s on the left. That leftmost bit is the sign bit, and a 1 indicates a negative number. The rightmost bit indicates whether the number is even or odd, and a 1 in the rightmost bit says the number is odd. Hexadecimal numbers are base 16 numbers. So for a base n, we need n symbols. For base 16, we need 16 symbols. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, and then A, B, C, D, E, and F. These are case insensitive, so a lowercase a is the same as an uppercase A in a hexadecimal number. That A represents 10, base 10, B represents 11, then 12, 13, 14, and a hexadecimal F represents a 15, base 10. The positions are powers of 16. The rightmost position is 16 to the 0th power. Any number to the 0th power is 1, so that rightmost position represents the 1's place. Then 16 to the 1st power, 16, 16 squared, 256, 16 cubed, 4096, 16 to the 4th, 65, 536, and so on as high as we need to go. Mostly you will not do work directly with 16-bit numbers in computing. Instead, you're going to use 16-bit numbers as a shorthand for binary numbers. How high can we count in 4 bits? 15. How high can we count with 1 hexadecimal digit? Also 15. And so 1 hex digit is exactly equivalent to 4 binary digits or bits. Let's look at the table. Binary 0000 is a hex 0. Binary 1 is a hex 1. Binary 2 a hex 2. Skipping down, binary 7, 0111, that's a hex 7. 1000, that's a hex 8. 1001 is a 9. And then we get into letters. 1010, A. 1011 is a B. 1100 is a C. 1101 is D. 1110 is E. And 111 is F. You do not have to memorize this table. If you work with hexadecimal digits, you will eventually memorize it. But you could recreate this on the back of an exam paper by writing down the binary integers 0 to 15, 0000 to 1111, and then writing 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, A, B, C, D, E, F right beside them. Remember that hexadecimal numbers are case insensitive. So a lowercase a is the same as an uppercase A, also for B, C, D, E, and F. Translating hexadecimal to binary, I just write down 4 bits, 4 binary digits per hexadecimal digit. So if I have a hex 17, I can write 0001 for that 1, and 0111, the binary 7, for that 7. To go from binary to hex, on my binary number, mark the bits in groups of 4 starting from the right, and write 1 hex digit for each group of 4 bits. So let's do one. Here is hexadecimal to binary. I have an AbleFox23 base 16. That 3 is a binary 3, 0011. 2 is a binary 2, 0010. F Fox is a binary 15, 1111. A is a binary 1010, which is equivalent to the decimal 10. To go from binary to hex, I mark the bits off in groups of 4 from the right and write one hex digit for each group of 4 bits. And that is everything I have to say about both 2's complement numbers and hexadecimal numbers.